Let's give some examples. Just to learn how we're going to deal with this type of, okay? So I have to review this story that I talk about it is regarding those roots of calculus. We need it. Okay, recall that this is what we did before. Recall that if the rate of change, we're going to define mathematically exponentially growth and decay first. So if the rate of change okay, rate of change of the variable, I use the notation of your book. I go with the y, but in your book they go the p in this one. Okay, recall that if the rate of change of the variable p is p for population, that's why we use p. Okay, is proportional. Okay, it's going to be proportional to the value. P. This means, see, this is what we mean. Rate of change is the derivative. Variable is p. So rate of change, dp dt, proportional to the p means it's a portion of the p, fraction of the p. So it's a k times p. That's the model. Okay, rate of change of the change of the population, unemployment, money in your bank. So this is going to be the case. Now, if you solve this one, it's easy to solve, okay? So, and then the solution, you can move the dt to the other side, okay? Take the integral, you get dp over p, there's gonna be ln involved, and then eventually this is gonna be the solution. Then the solution of the equation, okay, solution of the equation is the one that we did in calculus. P of t is equal to the a e to the kt. A is a constant, it's the initial value, initial population, initial money. Because if you put p of 0, e to the 0 would be 1, so that gives a. So a is equal to the p of 0 is the initial value. In this case, it's going to be initial population. Okay, initial population. So the formula usually given in this form. Okay, they call it P of t. P of t is equal to the P of 0. Okay, P of 0 e to the kt. Even sometimes P of t is equal to the P sub 0 e to the kt. So that's a model for this type of population that we have. If k is positive, you have the growth. If the k is negative, you have the decay. Okay. So if k is positive, if k is going to positive is an exponentially increasing function. Okay, then P of t equal to the P0 e to the kt is going to be exponentially, okay, it's going to be exponential growth. Otherwise, it's going to be decay. Okay, exponential growth model. That's the case. If k is negative, you have the exponentially decayed. Exponential. Okay, decay. So this is what we know. The easy method. Usually percent per given, you're going to pay. Now we want to extend this one. Okay, that's an easy equation, and we did it before. So this is where you let the growth go on freely. Okay, whatever. Yes.
You scroll up or you move the upper keys.
What?
So both k and t depend on the equation or on the question. So like K and T aren't set values that like are,
K is gonna be the, yeah, K from one problem to the problem would be, K is the rate that will be given to you. If you put the money in the bank, it's gonna be your 4%, 2%, 3%.
T is time.
T is time. So your job, if you want to set up this equation, is your job is to find P of 0 and K. See, if you find these two numbers, then you have a month.
P is 0 is the initial value.
P0 is the initial value. It's mostly will be given to you. You say, oh, I start by having, $1,000 in the bank, and the bank give me 2% interest. So as soon as you have the two numbers, you have your mother. Then what's going to the question? I would like to know how much money is going to be in my account after 5 years.
Solve for time.
Or how long do I have to wait? You see, how long do I have to wait for my account to be mature into the $10,000? Then you put P of T, A of T equal to $10,000, then you solve for T. And you have to determine the K and the P of 0 all the time first. And they give you something, you'll be able to do it. Okay? So from one problem to the other one, that two numbers would be different. Otherwise, the rest would be the same. Okay, any question? Now, what would happen if you change it? The change is going to be, you see, in this case, you didn't get any restriction. You just assume that the growth can go on forever. It's not the case. Okay, you don't like this population grows forever. Okay, so what you do is you are going to put down restriction. When we restrict it, you are going to have the following equation. Okay, so this is going to be the case. I'll just explain again this for you because it would be brief. You can study this one when you get to the next part. Okay, so there you are. What we are going to do is we express that the exponential growth, in this case that we have, is unlimited. You have no restriction, you can go on forever. But if you want to put some restriction, if there is some restriction would be you look at your facilities. So I can have up to the 1 million people in my place. Okay, so that's restriction you're going to think about. So if there is some upper limit, if you like, upper limit, we call it M. That's the maximum that you can afford, if you like. Okay, if there is some upper limit M, okay, that's it. It's going to be given to you some upper limit M, which growth can go up to the, okay, which growth cannot occur. If you pass the M, you can't do it. Okay, then there is an expression for M, then M, okay, M is going to be called, you have to know this expression for the problem that we have. M is going to be called the carrying. It's going to be called the carrying capacity. Okay, carrying capacity. It's expression. Or in this case, it's going to be maximum population. Maximum population. So you determine, okay, in advance, how much can you afford? How many people can you have? Now, what is going to be the nature of the equation? There are different models. For this form, we are going to consider the following, okay? I'm going to go to the next page. Ready? So one popular one to put this restriction is the following. Then, okay, upper bound for your term. And a model that's going to be used. Okay, the model that is used. MS1 is the following. Used to describe. Okay, to describe this type of situation. Describe this type of, okay, This type of growth. This type of growth is going to be called is the name is the logistic. Is the logistic differential equation. Logistic differential equation. And that's it. The rate of change, you see, dp dt. Previously was k times p. Now it's going to be k times. It's going to be k times p, as we did before. Now the restriction is going to be times it by 1 minus p over m. This is the general form of the logistic equation. These k and m are going to be your constant. K and m are going to be positive constant. K positive constant. Positive constant. Okay, this is the model that we're going to be interested in. And m is going to be the maximum capacity that would be given to the p. You know that the population, the rest are going to be the same. Okay, and we can prove that, you see, when we find the p of t. Of course, we solve this equation, we find the p of t. And if you find it at the end, we can prove that it can be proved. It can be proved that the limit of p of t, the population, when t goes forever, can you guess what's this number? Ahmad? M, you are right. See, because the maximum that you can have, the maximum population that you can afford, is going to be m that you start with. So if your solution is going to be correct, that's a confirmation. Your p of t is going to be your mother, the population. So this population cannot go on forever. So if t goes to infinity, automatically you should get m. Okay, you should get m, and you know that this is the case that, you know, and the growth, if you like. And the growth in this case is going to be limited. So that's the difference between the one that we did and the one that we created here. Okay, any question? So that's one. There are different ways that they are going to, okay, depends on the given problem that you can restrict it. The equation is going to be different. It's going to be different. They are going to be given. Okay, so this is the general one that I'm giving you. So what we'd like to do, we'd like to solve it. We'd like to solve it to find that p of t. In the previous case, remember, in the previous case, the p of t was just what? P of 0 e to the kt. Now let's see what's going to be this model. Okay, this is what I was talking about. I solved this one, logistic one. We give you the condition would be given to you. You can use the idea. You should have it. The p of t that I'm going to prove for you, but we give you something very mild. We give you the modeling, then you do it yourself. Okay, yes.
Is this like pretty much a curve that like concaves up and then like concaves down as it approaches the limit of m? So it's like,
Which one?
I don't know, d of p over d of
You have
t.
to find p of t first. When you find the p of t,
Yeah.
then you can, you know, you can describe it.
Okay.
You get these numbers.
Like, it wouldn't be like exponentially growing and then decaying. No. It would be exponentially.
So you see, it's going to be, it's like when t goes to infinity, you should you're checking the behavior of p of t when t goes to infinity.
Yeah.
So if it's going to be a function type, in that case, you have y equal to the m. Y equal to the m would be asymptote.
Yeah.
So that gives you exactly what will happen to it.
Good.
You know that when t goes to infinity, this is what your curve becomes. So this means that t goes to infinity, your p of t would be just like a line, y equal to the m.
But it's like forever approaching m though. It doesn't reach m.
Oh no, you don't have the phi of t. So you have to have the p of t, then you describe concave, then concave. But as is, you can easily describe it.
Yeah.
When the P of t goes to infinity equal to the m, this means what? This means with the graph of the function y equal to the m is going to be asymptote. This means when t goes to infinity, your graph becomes the line. That's the definition of the asymptote. Okay, let's solve it to see what that region of the function is. Okay, there you are. How are we going to solve it? So just learn the method that we described. But at the end, you need to use the equation. So solving logistic equation, logistic differential equation. Yeah. There you are. So this is it. Let's start with the equation. Have to check, simplify a little bit, separable variable to be able to do it. Okay. And so what I'm going to do, I'm going to take care of this side denominator first. These parentheses. Okay, get the common denominator, do the algebra because you want to put the t's in one side, dp and the dp on the other side, solve it as a separable equation. That's the way we want to do it. Okay, so there you are. This is how I'm going to start. It's going to be k times p. Common denominator would be m. So on the top, I'm going to have m minus p. Okay, this is it. Cross multiply it. So if I cross multiply it, so the m would be, I'm going to have the m dp. The mdp, so on the other side, it's going to be what? It's going to be kp times m minus p times dt. Okay, you want to write down as a separable variable. So you have to collect the p and the dp on one side of the equation and the p on the other side. So what are we going to do? So k is a constant, remember. So I need to bring this p and the d m minus p together with the dp. Okay, so I divide it. So this is it, m dp divided by separable variable. Okay, divided by the p times m minus p. The leftover is going to be what? The leftover will be k dt. Okay, k dt. Now this is a separable equation. It's an equation with a separable variable. Because your variable is going to be p and dp, or on the other side t and dt. So it is, okay, this is it. It's a separable equation. It's a separable equation. It's a separable equation in terms of, just remind you, in terms of what? In terms of the p and the t. Solve it. Take the integral of both sides. So what you have? Integral of m on the top, p times m minus p dp equal to the integral of the k dt. So you have the second part of the integral is easy. It's going to be kt plus c. And you have to work on the integral to the left. Okay, any suggestion? This one? Which method? Partial fraction. You have to use the partial fraction method. Okay, so let's work on the partial fraction one. You can pull out the m, okay, or just try it. So I'm going to try what is going to be m over p times m minus p. So you are going to have the p and you are going to have the m minus p. That's it. You need to have m on the top only. So this is a p and negative p. So if you put the 1, 1, it will cancel out and you get the result right away. See, because that gives you m minus p plus p. So positive p, negative p will cancel out and you get there. Okay, lucky. So go back and continue. take it over here and integrate it. Any question? And the common denominator to give you the same thing. So this is it. So the integral would be changed into the 1 over p plus 1 over m minus p dp. Okay, dp. And on the other side, you have integral of k dt. Integrated. It's going to be respect to the p, so it's going to be ln p. The second part is respect to the p, it's a m minus p. So the derivative would be -1, so it's going to be negative. Okay, it's going to be ln of the absolute value of p minus ln of the absolute value of m minus p. On the other side with the kt plus, okay? And then I'm going to go to the next page. Take the integral. Okay, that's it. Integral first one was, you get ln of the absolute value of p for the first one. It's going to be minus because the denominator get m minus p, u prime is a -1. So it's going to be minus, and this is going to be ln of the absolute value of m minus p. Okay, n minus p, and on the other side we get kt plus c. Okay, this is what we get. Now we can simplify it a little bit, okay, to get through it. So I want to change it to the exponential form. So I'd like to have this one up in front. So I multiply by -1. So I rewrite it as absolute value of n minus p. This is going to be minus ln of the p. And this is going to be minus kt. Okay, minus kt plus c. Just multiply by -1. I want to simplify this. Okay, now this is going to be the difference between the two natural log. You know, the difference will be quotient. So it's going to be ln. Okay, it's going to be ln of the absolute value of m minus p over p. M minus p over p. And the other side would be negative kt plus c. So change it to the exponential form. The base of the natural log is e. So this would be what? It would be m minus p over p. M minus p over p is going to be e to the negative kt plus c. Okay, just definition of a natural log. Get this true. So we can break this one. We can break this one, and we can break this one. Simplify it. So this is what you have. You get m over p minus p over p. It's going to be e to the kt times e to the c, which is a constant. And this constant over here, we're going to denote it by a. Okay, that would be constant here. And the p and p would cancel out. So we get m over p minus 1. And this is going to be 8 e to the kt. A is a constant, okay? A is going to be constant, and so for p. So move the 1 to the other side, so that give you m over p. And this is going to be 1 plus a e to the negative kt. Okay? And solve it for p. You solve for p, you can switch these two to get the p. So it's going to be p. So your p is going to be m. Okay, m over 1 plus a e to the negative kt. So that would give you, that's it. So officially, p of t, the population, p of t is equal to the m over 1 plus a times e to the negative kt. This is going to be the solution of a logistic equation. Yes.
So is that basically saying that the denominator grows exponentially until it hits m?
That's it. Yeah. Now we quickly confirm it. When t goes to infinity, this would be what? This would be 0. Because it's a negative. It's a negative kt. okay, negative KT. So this would be zero, so you end up with that.
So it's
So quickly, we note that. Note that if you find the limit, okay, if you find the limit of P of T, limit of P of T, T goes to positive infinity. Okay, so this is going to be the limit of M over 1 plus AE to the negative KT. And this part goes to 0 now. Because the power is negative. To the negative infinity, okay? And T goes to infinity. So the result would be M, as we predicted. It should be M squared. Because the maximum population is, so P of T, T goes to infinity, is equal to the M, and this means you have a, okay, you have a nice model to work with. Yeah, that just show you the way you are going to know. If it's going to be given to you, the way you are going to, okay, you're going to work on it. The model that you have are either separable variable or it's a linear one. One that we have, I'll give you one linear, then you can see it. The linear is very easy to see when it's given to you. The linear one is the one from the electrical circuits. We are going to do that. Okay, so this is one type. You can use this solution, okay? You can use this solution as a logistic equation. So we are going to give you some information. Remember, in order to be able to do this one, to work with this, okay? So you have to set up this equation first. In order to set up this equation, that M would be given to, because this is a maximum population. So the maximum population would be given to, this A would be given also. Okay, and then what you have to do is to set it up. Sometimes you have to find the K yourself. So some information will be given. It's a population. So population after 5 years, the population is 10,000. So you have to set up these numbers and get it right. Then they ask you a question. Okay, what would happen for the population growth after 20 years? You just substitute and get it. So the setting it up is going to be easy. Okay, I can give you a break now. Come back, give you one example, and then we try one more. That's from electrical circuit. So the situation is a state needs gain commission. Okay, state commission. I have to explain the problem. Okay, commission releases. Okay, releases 40 elk into animal conservation into game refuge. Okay, we'd like to keep these kind of animals and take care of them, preserve them if it's the case. So we start with the 40. So after 5 years, the population will grow. Okay. So after 5 years, population is 104. So initially you have 40, after 5 years you get 104. This one shot is going to be for you to be able to find the K. Now the commission believes, the commission believes that that's environment environment can support no more than 1 than 4,000 years. Okay, so this is going to be the most that you can afford. Okay, kind of a maximum. Limitation. So the limitation that you have is going to be the minimum you have 40, but the maximum is going to be 4,000. Okay, so the model for this one is already given. The growth. Okay, the growth rate. This information you can put them together. It's a logistic equation. So the growth rate of this population is given by, you see that's it. Rho P rho T, the rate is going to be equal to the K times P times 1 minus P over 4,000. Okay, that's it. And the P is between 40 and 4,000. So as you can see, if you compare it with the formula that we talked about, this is going to be a logistic equation. It's going to be logistic equation, and if you check the formula that we gave you, this was P over M. And over here, so quickly you have to take these numbers out, your M would be 4,000. So, and with the unit for the T is the number of years. T is the number of years. So this is going to be rate of the population growth of those, okay. So what's the question? The question is going to be a couple of things that they ask you to express. First, write the model. Okay, write the model means find P of T. Okay, model for the elk population. Elk population. In terms of, okay, in terms of T. So basically this means find P of T. You recognize this is going to be a logistic equation and you already got the formula for P of T. The formula that we prove, P of T equal to the M over 1 plus A e to the negative. That would be your model. Okay, that's a step one. Step two, they wanted to work in the model. Okay, use the model, use P of T. Use the model. Okay, use the model to estimate. Okay, to estimate the elk population. Population after, okay, after 15 years. It's easy. The time is given to you. If you have P of T, you want to find P of 15. Substitute here. Okay. And the part C, they usually ask for confirmation. Find the limit. Okay, limit of the model is P of T as T goes to infinity. And we know that limit should be the maximum number, which is 4,000. That's it. Okay. So we identified that's a logistic equation, and we know the result of the logistic equation model. Okay. So solution is going to be, okay, the growth rate population is a logistic equation, and then we bring in a solution. So note that in this case, the solution is going to be P of T equal to P of T equal to the M 1 plus, okay, 1 plus A e to the negative KT. That's it, and T, mention it, is in years. That's your model. Okay, now you have to, you know, this equation, you have to find those numbers, okay? You need to give us the M, A, and K. Then you have to model for this problem. Okay, you go back and you collect the information that you have. Okay, the maximum is going to be maximum of the population that you can have. Restriction is 4,000. Okay, so get these numbers. So M is equal to the 4,000 maximum. Then in order to find the A, you need to check the initial value. So initially at the beginning, you start with the 40. So P of 0 is equal to the 40. Okay, and quickly you can apply this one to get the A. Okay, this is going to be the case. So go back, substitute to get these numbers. P of 0 equal to the 0. Okay, so we get it from here. And we get T equal to the 0 here. So we can start with the P of 0, which is 40. Okay, 40 and M is 4,000. M is 4,000. This is going to be 1 plus A. This would be E to the 0. Okay, E to the 0. So again, get a 40 equal to the 4,000. And this is going to be 1 plus A. You can cross multiply or just divide it by 40, then cross multiply, get the result. Okay, divide by 40, that give you 1, and that give you 100. So cross multiply 1 plus A would be equal to the 100. So A would be 99. Okay. So that give you the case. So go back and then you have to work for the K to get these numbers. Okay, any question? So I'm going to go back and substitute here. Okay, because I got the A and I got the M. Okay, these two are available. And I have to do something to be able to get the K. And do it step by step, okay? So go back, substitute in your model. So what we have so far. So the model is going to be so far P of T. Okay, P of T, M is 4,000. M is 4,000 plus 1 A. A is 99. Okay, A is 99, and you get E to the KT. So you have to find the K. As you go back to see what you have, you see the information is initially after 5 years. 5 years, okay. The population is what? P of 5. After 5 years, the population is 104. Now we're going to use this one to get the K. So you substitute in your model. So that gives you 104 equal to, get the 4,000 here. Okay, 1 plus 99. 99 e to the T is 5, e to the negative 5k. We have to solve this one to get the k. Must multiply and use your calculator to eventually get the result. So it's going to be 104 times it by 1 plus 99 e to the negative 5k and plus 4,000. Okay, you may use your calculator. Okay, it's going to be 1 plus 99 e to the negative 5k, and this is going to be 4,000 over 4. Okay. And you can simplify it and eventually get the result. 99 e to the negative 5k is equal to the 4,000 over 104 minus 1. You can simplify it by 4 and then continue, or just keep it as is. If simplified by 4, so that give you 20, 24, 23. So that give you 1,000. Okay. This is it. So that give you 99 e to the negative 5k. You can use calculator to accept it. 23, that's going to be 1,000 minus 23. Okay, it's gonna be 23. Give you 7, 7, 9. And we get e to the negative 5k divided by 9, 7, 7, 23. And divided by 99. You have to use your calculator to get this one. Take the ln on both sides to get the, okay. So negative 5k is going to be ln of 977 and 23 times 99. And k would be negative 1/5. ln of is the number. Check it in your calculator, I have 0.194. So k equal to the 0.94. Check it, make sure you get the same number. Yes. Okay, now the model is complete. Go back, substitute, and you get a P of T. Okay, remember it was M, which is 4,000. 1 plus A is 99. This is going to be e to the negative. Okay, e to the negative 0.194. See it? Of course, t is in years. So eventually, this is going to be the model of your population after 10 years. Okay, they ask for the P of 15. What will happen after 15 years? So you have to substitute t equal to 15. Use your calculator, get the number. To run that because this is the number of the population. Okay. Any question? So it's not a difficult procedure, but we got to be careful. So we would like to find what is going to be the population after 15 years. So substitute P of 15. Okay, P of 15 is going to be 4,000. That's going to be 1 plus 99 e to the, this is a t here. Okay, negative 0.194 times 15. Okay, in user calculator, I have 626. Population after 15 years. It's very nice. You start with the 40, and now you get 626.
Do you round,
Yes.
do you round up or round down?
Which one?
Do you round up or
It's a
round
number
down?
of it's animals.
But it's like, it's 625.67,
So
So do you run up?
so it's 26.
but you wouldn't have 2/3 of an elk become a full elk.
Can be a baby elk.
Or is it a baby?
No, we
Yeah,
just use common sense.
Yeah.
26. Yeah, that's right.
It's giving birth.
Okay, and
It's mating season, so it's almost there.
It's 2/3.
part C is the confirmation. You have to show that the limit of P of t goes to infinity would be m, which is 4,000. And that's clear, you see it well here. When t goes to infinity, that exponential part would be 0. 0, so we get 4,000, okay? So I put the part C here. Okay, that's it. So the limit of P of t, t goes to infinity, is going to be equal to, got it over here, it's going to be equal to the 4,000. Equal to the m, which is 4,000. So we know it from the theorem, but we have to have a look at it to make sure that you get it right. Okay, so it's a very popular case. As I told you, we give you one, but we give you a mild one. We create a kind of a equation, then we ask you to do it yourself. Equation. It's not going to be a difficult one. So I'd like to give you one more to see, just for, to see what is going to be other. Most of them are going to be separable variable. But in the application, linear equation is going to be around, especially if you go with the electrical circuits, okay? So there is a property. We know that, better than me, you know that there's going to be Kirchhoff theorems talking about, those contextual, etc. So I'm going to set it up this equation and show you. The only thing that we are interested in, just the model would be given to you. And this is a linear. It can be very messy, this one. Let me show you. It's not the type that you'll be able to memorize it. Because in the one that we did over here, everything was set up nicely. You cannot do much about it. Just changing those numbers. But sometimes you have to know the result or the techniques, okay? Let's give you this one. It's a very unique one. That's to show you how you're going to do it yourself. Not that match, okay? But the one that we gave last semester, everybody was able to do it right away, okay? So another case from, this is the case from, we call it series circuits from physics. Okay, I have to explain this one as much as I can. So this is the situation I'm going to have. There is going to be a circuit over here consists of an inductor. So that's going to be the inductor. Okay, then there is going to be a voltage over here. You are going to measure the electricity. Okay, and in between over here, there is going to be a resistance. Okay, we have physics. And so this would be denoted by L, and this is going to be your inductor. And the measure for this one is 100. This is going to be resistance, which is going to be R. So this is going to be resistor, if you like. And the measure is going to be ohm. And over here is going to be just electricity, this is voltage. Okay. Now we're going to apply the so-called Kirchhoff law in this one, and everything would be given to you. Okay, I'm going to describe it. The description is going to be in this series, series circuit containing only a resistor. Okay, we have a resistor, as you can see, and an inductor. And inductor. Then we are going to apply the Kirchhoff law. So Kirchhoff. Kirchhoff, so-called second law. That law states that the following, it's about rate of change. State that, so that's going to be the law that the sum of voltage, the sum of voltage drop plus, okay, plus the inductor plus the inductor, they denoted by L times di dt. L is going to be the constant that we use for the inductor. That would be given to is a constant. Measurement is 100. Then I is going to be di dt. It's going to be the rate of change of the voltage that we're going to have. Okay, across the Li, and So the sum of the voltage drop, so this is going to be voltage drop and something else. And the other one is, so the sum of the voltage drop across the inductor and the voltage drop across the resistor. The resistor. This one will be denoted by I times R. Is the same as impressed. It's all physical, expression. Impressed voltage E of t on the seconds. So basically, this is what we are interested in. The result is the differential. You see the sum of the L di dt less Ri or IR, R times I is equal to the E of t. See, this is the differential equation that we're going to be interested in. So I is going to be just intensity, it's going to be your function, is a function of t. L is a constant, R is a constant, E of t should be given to you. That E of t is the one that, would be changed. You cannot memorize the result of this equation. Because E of t can be constant or E of t can be given in terms of the function like sine or cosine. Okay, but we're going to consider one constant case. So this differential equation is the one that you usually use in this type of ideas. As you can see, this is a linear equation because di dt is like I prime. So it's going to be I prime. This is constant. So if you want to solve it, you have to apply the procedure for the linear equation, but the notation is unusual. Then you'll be able, you'll be able to do it. So this is going to be the case. So these constant, where L and R are going to be given to you, are going to be constants. Okay, that it's going to be constant as the inductor and the resistance, respectively. Okay, as this is coming from that inductor. Okay, we call it inductance. And the resistance, what number would be given? Okay. And the current is going to be a function. Okay, the current I is a function of t. I of t is going to be called, response. It's going to be called the response of the system. Just want to give you something, from logistic equation is easy. Okay, so we can solve it if you like, as is. That it's not going to be fun. You get a formula, but we better take it as and it's given to you, and E of t would be given because it's clear. You see your as is. What do you have? You have to divide by L. When you divide by L, you identify your P of t in this case. P of t is a constant, will be R over L. You have to find the integral of the px dx, and then exponential one, and just put them together. So as an example of this format is going to be the following, okay? So I'm going to give an example. I give you the L, R, and E of t, and then ask for the, for the current at some points. So this is going to be the modeling that we have. Okay, any question? So if this type of problem would be given to you, we directly give you the differential equation. Okay, I'm going to describe the situation that we have. Okay, so we are going to put it in action of two functions. In the real life, that E of t is going to be, okay, you did have a calculus too. integral of 2x sine of the 5x, this type of integral, e to the ax sine of the bx. We are going to use it for the Laplace transform later on. But for this type of problems, if one gets serious, that e of t in the real life is going to be always of that format. And then when you want to find the integral of the mu qx dx, you have two choices. Either you memorize the notion of these integrations that we are going to give you. We are not going to give you in this course, but then you get to the Laplace transform. We'll just change it to the Laplace transform to do it, if you are going to be measuring this type of ideas. But the one that we're going to talk about it, we take ET to be constant. Okay, so it's avoiding this. But that would happen for the real life. Okay, there you are. This is it, a 12 volt. Give you those information, 12 volt battery. Okay, battery is connected. It's going to be connected to a series circuit. Series circuits in which you have to give you the inductor, in which the inductance means L. Inductance is 1/2, measurement is Henry. 1/2 Henry, and the resistance means R. And the resistance R is 10 ohm. And this is going to be the unit for the R. Okay, so this is going to be L, this is going to be R. Say this is your L, and this is going to be your R. Quickly, you can set up that equation. You need to be given the, that's it, and this is your voltage is going to be your E. Everything is already given to you, so they ask for the current. So whatever you want to do is determine the current I, give the initial value, the initial current. Initial current is 0. So this means what? IE, this means I of 0 is equal to 0. Okay, just know these expressions. So you know the differential equation. We talk, but see the solution would be. So we use the Kirchhoff law. By the Kirchhoff law, you have L di dt plus R times I equal to the E of t. That's a differential equation that we created using the Kirchhoff law. Now substitute. Your L is Henry, is 1/2. R is equal to 10. Your E of t, this is what I talk about, will be equal to 12. Substitute, so that give you 1/2 di dt, okay, plus 10 times I equal to 12. Easy equation to solve. Respect to the I and the t, this must be a linear equation. You have to take care of the 1/2 first. So multiply by 2, make it to the standard equation. So that give you di dt plus 10I. If you like, this is I of t equal to 12. It's a linear equation in I and t. It is a linear equation. In I and t. So P of t is equal to 10. Q of t is equal to 12. I of t is the missing one. Yes.
Are you supposed to multiply by 2 for the entire thing? So it'd be 10.
Oh, I didn't do that. Oh, sorry. Thank you. So that would be 20 That would be 20. Thank you. Okay, 20,
I think that's what he's saying.
24.
Function for I is take off.
Okay. Everything else all right? Tomato. We'll start working on the solution. Integral of PT dt. Okay, that's it. You get the 24 is correct. Okay, so fine. Yes,
How does 10i become a function of t or 20?
I is a function of t. I just emphasize that this is a function. Because in this problem, you see the current is a function of t. It's like, you know, when you work with the differential equation, you get the y and x. In this case, your y is I, but I is a function of t, which is time. Just emphasize so that when you integrate it, you know that everything is a function of t. But this e of t over here is a constant. Okay, so work on that equation, integral pt dt. It's easy, it's a 20 dt, so that give you 20t. That's going to be your pt. So integrating factor for this e to the integral of e to the 20t is going to be the case. So going to the formula. Okay, that's it. I of t is going to be equal to the 1 over. Okay, 1 over mu. I just remind you, it's going to be 1 over mu, and that's going to be qt mu dt. So this is going to be equal to the 1 over e to the 20t integral of Q2 is constant. Okay, it's 24. It's going to be 24, and it's going to be e to the 20t dt. So this is what we have. It's easy integral to find. Okay, you can move this one up. So what we have, you get I of t is equal to the 24 e to the negative 20t, and exponential function never change, e to the 20t, but you have to divide by 20. Okay, plus the constant c. Okay, you can only subtract a little bit, otherwise you're done. You can multiply inside and simplify it. So that give you I of t equal to, okay, multiply this inside. So that give you what? That give you, this would be 124, 24 over 20. 24 over 20, and the plus, the leftover, you can call it c altogether. Okay, multiply this together. So that give you plus c e to the negative 20t. So that would give you the, okay, the type that we have. Any question? So you can, don't have any more information. Okay, that's going to be I of t, and you have the initial value. Initial value is 0. So I of 0 equal to the 0. You simplify everything, and this would be what? I of 0 is equal to the 0. So that gives you 0 equal to 24 over 20. Okay, plus simply plus c. So c would be negative 24 over 20. So you go back and you substitute c here. You can factor it out if you like. You get the final answer. Okay. So I put it here. Final answer. I of t is going to be equal to 24 over 20 minus 24 over 20 at e to the negative 20t. Okay, you can call it out or just write it down as yeah.
Can you distribute the 24 to the c, 24 e to the negative 20t?
Constant is a constant.
Because initially you go back and find what c is going to be the same. Okay, so then this that give an idea that if it's going to be randomly, it's given to you can do it. You have to be patient because the notation is different. Okay. Okay, position will be different. Okay, so that's just to give you a taste of these numbers. There is one that we talk about it when we get to the system of calculation. Just show you this one. Yeah, I'm going to give this one as those other project that we have. You see, there is something we call it. This is it. Predator prey model. You know that there are some creatures that they feed on the others. Okay, so in this case, there are going to be the example that's considered are going to be foxes and rabbits. Okay, so there must be a balance between these two. The rate of change, rate of increase of the foxes and the decrease of the rabbits. When you put them together, that give you a system of the differential equation. You see, we're going to learn. This is going to be two different rates, and talk about this one when we get to the end of the course. Okay, so we are ready for the test. Test on the next class.
Wait, what?
Yeah, I already posted.
Oh, 20. Isn't it Tuesday? Oh, review, test review. I
Test
thought you
review.
said
I've
10.
already posted, okay, the review. And there is going to be one for you to do for your extra point.
Oh, yeah, no. Yeah, it doesn't look too bad. I'm just gonna. Four last time?
Practice quiz is really hard.
Yeah, some of those don't have.
Last quiz.